going to be working with solutions for 4.1. I'm going to skip the first set of problems here just because I'll probably cover most of that in class. I'm going to start here at number 23, and we are given a function f of x is equal to 4 plus 1/3 x minus 1/2 x squared. And we're asked to find the critical numbers. So we basically want to know, we want to find where that means at what x value the derivative is 0 or where the derivative does not exist. Or the derivative, does not exist. All right. So let's first take the derivative. The derivative of this function is going to be 0, and then derivative 1/3 x is 1/3, and then derivative of negative 1/2 x squared is going to be negative x. That's it. So first let's figure out where this thing is 0. The derivative equals 0 means 1/3 minus x equals 0. And if we solve for x, just add x on both sides. We get x is 1/3. And then if we want to know where the derivative is undefined or doesn't exist, then we need to figure out if this ever has any domain issues, if we ever get division by 0 or square roots of negative numbers or anything like that. But this is a well-defined function. We can plug in any x and we're not going to have any issues. So we don't have this happening at all. So the only critical number that we have is this here, x is 1/3. All right, for number 25, I'm going to do the odds, and then hopefully in class I can do the evens. So 25. F of x equals, and then 2x cubed minus 3x squared minus 36x. Same thing, we want to know the critical numbers. So I'm going to first take the first derivative of this. And the first derivative is 6x squared minus 6x minus 36. And now I'd like to know where that is equal to 0 and where it's undefined. So f prime equal to 0 means I need to set 6x squared minus 6x minus 36 equal to 0. We have a quadratic equation there. I also notice I can divide everything by 6. That'll make it a little easier for me. So divide everything by 6. And I believe I can factor this out and set each factor equal to 0. X is 3 and x is negative 2. So far I have two critical numbers. Both of those critical numbers, by the way, they do, the domain of the original function is all real numbers because it's a polynomial function, and therefore these critical numbers live in the domain. Later on we might have some issues where maybe one of these don't live in the domain, but for now it's fine. And then to figure out where this doesn't exist, I have to look at the quadratic function right here and just ask myself if there's any places where it's undefined or has problems. And it's a polynomial also, so it's defined everywhere, so I'm never going to have that happen. So these are the only two critical numbers. All right, number 27. G of t equals t to the 4th plus t cubed plus t squared plus 1. All right, so first thing, I take the derivative, g prime of t. This is 4t cubed plus 3t squared plus 2t. And now I'm going to figure out where is that derivative equal to 0. So I set this polynomial equal to 0. I factor out a t. I notice I can do that. And now I go about trying to factor this quadratic. I do not believe that's going to factor, so what I'll do is I'll split this up into two separate problems. All right, t equals 0 is one answer. That's one critical number. The other one, or any other critical numbers I get, are going to be the solutions to this quadratic. So I'll use the quadratic formula here. T is equal to negative b plus or minus square root b squared, all that stuff, right? So negative b plus or minus the square root of b squared, which is 9, minus 4 times a, which is 4, times c, which is 2, all over 2 times a, so 2 times 4. And notice here I get 16 and then 2, so 16 2 is 32. 9 take away 32, that's going to give me a negative number underneath the root. That means I'm not going to have any real number answers. They're going to be just imaginary numbers. So I do not have any real solutions from this. So I'm done with that. And then I move on, where is this undefined or does not exist? And again, because the derivative is a nice polynomial function, we won't have any issues at all. We'll be good to go. So for 27, the only critical number I have is 0. All right. (29) g of y equals y minus 1 over y squared minus y plus 1. All right, so we want to know where we have any critical numbers here. And the derivative of this is going to require some quotient rule. So I do derivative of the top, which is just 1 times the bottom, minus the derivative of the bottom, which is 2y minus 1 times the top, all over the bottom squared. All right, so I'll have to multiply things out. This is going to be 1 passes through here, you just get y squared minus y plus 1. And then I'm going to get here 2y squared minus 2y minus y plus 1. So this is 2y squared minus 3y plus 1. But I'm subtracting this, so I'm going to change the signs on each of these. So I get negative 2y squared plus 3y minus 1 all over y squared minus y plus 1 squared. And then I can go a little bit further. I can combine any like terms together. So I have y squared and negative 2y squared, which is going to be negative y squared. So I've got those taken care of. The y's, I should have negative y plus 3y is plus 2y. And then as far as constants, plus 1 and minus 1 cancel. So that's it. That's all I've got on the top. And on the bottom, I have the denominator y squared minus y plus 1, that quantity squared. So there's my derivative. So now what I want to do is I want to figure out where that derivative is 0. So I take negative y squared plus 2y over y squared minus y plus 1, and I square that, and I set it equal to 0. And as I discussed in class, if you ever have a fraction equal to 0, you can always multiply both sides by the denominator, and since this is 0, basically the denominator is going to go away on this side, or it'll be 0 still on this side, and then you'll cancel out over here, and all you're going to really be looking at is setting the numerator equal to 0. And this is a pretty straightforward quadratic. I can factor out a negative y, be left with y minus 2, like that. And then set each of these factors equal to 0. If I set this to 0, I get y is 0. And if I set this to 0, I get y is 2. So I have two critical numbers so far. Now I need to figure out where this derivative doesn't exist. And so when we go back and we look at this derivative over here, where could I have some problems? Well, I could get division by 0. So I need to consider this. Does this denominator, does that ever equal 0? That's my question. If it does, if this actually has a solution, a real solution, then I'm going to have a problem and my derivative won't exist. So what I'm going to do is just see if I can solve this. I'm going to use quadratic formula. So negative b plus or minus square root b squared minus 4ac all over 2a, that same formula. Negative b here is going to be 1 plus or minus square root, and this is the most important part. B squared would be negative 1 squared minus 4 times a, which is 1, times c, which is 1, and then all over 2 times 1. And then inside here, you're going to see you have a problem. 4 times 1 is going to be 4. 1 minus 4 is negative 3. It's a negative under the root. This equation does not have a real solution, so that means you're never going to have the derivative being undefined. Therefore, those are your only two critical numbers. Okay, next one. Let's do 31. Capital F of x equals x to the 4/5 times x minus 4, that quantity squared. All right. Well, I'm going to need to do a derivative here. The derivative of this, I'm going to apply the product rule right here. There's your product. So it's the derivative of the first one, which is 4/5 x to the negative 1/5 times the second one, plus the derivative of the second one here is a chain rule. So the 2 drops out, x minus 4 to the first power. I don't need to write that, but I am. Then the derivative of the inside, so times just 1, I won't write that, times the first function, that'll finish off the product rule. All right, so there it is. Now let me try and clean this up. We haven't really had a lot of problems where we clean this up, but the thing is we're going to be setting this equal to 0. So let me try and rewrite this so it looks a little better. How about this? The 4 stays on top, this stays on top, this is going to drop down with the 5. So 4 times x minus 4 squared over 5x to the 1/5 plus the 2 stays, everything here stays on top, so I'm just going to write 2. I'm going to write x to the 4/5 first, and then x minus 4, like that. All right, there's our derivative. We need to set this equal to 0. We also need to figure out where it's undefined. So let me first set this equal to 0. Where is the derivative equal to 0? That's the question. So I said 4 times x minus 2 squared over 5x to the 1/5 plus 2x to the 4/5 times x minus 2. When is that equal to 0? So what I've recommended you do in a problem like this is try and put these two terms together, get a common denominator. So I'm going to look at this as being over 1. And that means I'm going to have to insert here myself the, let me see, I'm going to have to insert in here a 5. So I'm going to multiply the top and bottom here. I'm going to move this equal sign out just a little bit. I'm going to multiply the top by 5x to the 1/5 and the bottom by 5x to the 1/5. Then I'll have the same denominators. So what will happen is I'll have the 4x minus 2 squared, that's this, plus this new numerator with all that together. So watch. 2 times 5, that gives me 10. So I'm going to go plus 10. X to the 4/5 times x to the 1/5. You add the exponents. 4/5 plus 1/5 is 5/5. That's a 1. So I just get x to the first power. Then I still have the x minus 2. Then all over my common denominator, which is 5x to the 1/5. That needs to be equal to 0. Now I have a single fraction. And the only way a fraction can be equal to 0 is if the top's equal to 0. So now I just write the top, the numerator. Equals 0. And I need to solve this. Now you could expand this out and then collect like terms and multiply that through, but I'm just going to realize I have an x minus 2 here and here. And I also have some other things. I can pull a factor of 2 out of each of these. So if I pull a 2 and an x minus 2 out, I would have a 2 here from this 4. One of these factors is pulled out, so I still have one of them. Here I pulled out a 2, so plus 5. I still have this x. This x minus 2 got pulled out, so that's all that's left there. Now this in here is pretty clean. I just distribute the 2 through. I get 2x minus 4, and then I have plus 5x. So here's where I'm at. I have 2x minus 2, and then in here the 2x minus 4 plus 5x is going to be 7x minus 4, then equals 0. And now I can set these factors equal to 0. Of course, we can throw this out because that's never going to be 0. Set this to 0, we get x is 2. Set this to 0, we get x is equal to 4/7. So it looks like I have 2 critical numbers so far. Hold on a second. What did I do? Did I write the problem down right? Yes. Wait a minute. Hold on. I just realized something here. I switched this to an x minus 2 somewhere in the middle of the problem. Uh-oh. Let me fix it. I apologize ahead of time. You probably caught that earlier. I was setting that equal to 0. I was supposed to be setting 4x minus 4 squared over 5x to the 1/5 plus 2x to the 4/5 times x minus 4 equal to 0. Wow, how did I mess that up? And then I multiply the top and bottom here by 5x to the 1/5. Here's a 5x to the 1/5 here. This gives me 4x minus 4 squared. It's going to be all over. Now, when I multiply these together, I get plus, this is still 5 times 2, that's 10. It's still x to the 5th times x to the 4/5, that's still x, but now I have x minus 4. All right, and then over the common denominator, which was 5x to the 1/5, equals 0. Then all I have to do is set the top to 0. So I apologize, I don't know how I messed that up. I'll have to go back and look at the video to see what I did. So all I have to do here is set the top equal to 0. So forget that for a minute and just set that equal to 0. But I can factor out a 2 and an x minus 4 this time and be left with a 2x minus 4 and then a plus 5x equals 0. So I pulled a 2, since these both have a 2, I pulled one factor of x minus 4 out, and that's what I should have. And then 2x times x minus 4, and then when you do this and this, you'll get 7x minus 8 equals 0. And that means you're going to have 2 different answers. You're going to have x is equal to 4, set that equal to 0, forget this one. And then x is equal to 8/7. All right, those are our two critical numbers so far. Now I still need to figure out where the derivative might not exist or where it's undefined. And for this problem, we actually do have an issue. If we go back and look at the derivative, you can see that at 0, if I plug 0 in here, I'm going to get division by 0. And that's a bad thing. So I just by inspection can tell that x equals 0 is going to be another point that causes an issue for the derivative. Now this point is okay to plug into the original function. So this critical number lives in the domain of the original function because I don't have division here. So you can plug 0 in here and 0 in here and that's fine, you can get an answer, but you can't plug 0 into the derivative. So there is a problem here. So now I have 3 total critical numbers. Let me just check this real quick. F of theta equals 2 cosine theta plus sine squared theta. All right. Let's talk a little bit about the domain first. The cosine function has a domain of all real numbers. The sine function has a domain of all real numbers. So the domain of the original function is all real numbers. Let's take a look at the derivative. The derivative of this is negative 2 sine theta. So that's just derivative of cosine is negative sine. The 2 comes for the ride. This is chain rule. 2 drops out, so plus 2 sine theta to the first power. Then times the derivative of what's down here, so derivative of sine theta is cosine theta. So there's our derivative. Now let me set this derivative equal to 0. So to do that, I set negative 2 sine theta plus 2 sine theta cosine theta equal to 0, and this is why we took pre-cal, so we could solve these things. So to solve this trig equation, I'm going to notice a common factor. I have negative, or I can do negative or positive, it doesn't matter. I'll do negative 2 sine theta as a common factor. Pull that out. If I pull that out of this, it's just a 1 there. And if I pull a negative out of this, it's going to be negative. The 2 sine theta came out, so I'm just left with cosine theta equals 0. And now I can set each of these equal to 0. So I need to set negative 2 sine theta equal to 0. And I need to set 1 minus cosine theta equal to 0. Here I can divide both sides by negative 2 and just get sine theta equals 0. And over here I can just move the cosine over. I get cosine theta equals 1. All right, now we are not given a domain in this problem, right? We are not given any domain restrictions here. It's very important that we're not. That means that when we're trying to solve this trig equation, we need to take all solutions into account. So you need to ask yourself, where is sine theta 0? So you go back to your unit circle. Sine is the y coordinate on the unit circle. And you want to know when the y coordinate is 0, and that happens here and at here. So we need to represent all possible answers. We're saying that this angle theta could be 0 or pi, or you could have 2 pi or 3 pi or 4 pi. You could have also had 0, negative pi, negative 2 pi, negative 3 pi. So what I suggest in my classes is that you pick one of the angles, okay, that's 0. So theta must be 0, and then plus whatever rotation it takes to get you to the to jump around from one solution to the other. So I have to add a pi to get to here, then add another pi, and then add another pi, or I could subtract pi's. So what I'm doing is I'm taking 0 and I'm adding any multiple of pi. And let's see, the book uses k or n. Different books use different letters. They want you to use n here. So 0 plus any multiple n pi. And then you really don't need the 0, okay? So you can just write n pi. So every multiple of pi, 0 pi, 1 pi, 2 pi, 3 pi, negative 1 pi, negative 2 pi, negative 3 pi, all of those are critical numbers. And then over here, cosine is, theta is 1. Cosine is the x coordinate, right? And that's 1 here. That's the only place it is. So again, what I could do is I could say theta equals 0. That's my initial angle here. And then how do I get back to this point? Well, I could add a full rotation, that's 2 pi, or another full rotation, which would be 4 pi, or I could go backwards 2 pi, or backwards 4 pi. So I'm going to be adding n times 2 pi. So any multiple of 2 pi plus 0, which is my initial starting point, should be an answer. I can just rewrite this as 2n pi or 2 pi n. It really doesn't matter. We like to put the letters behind. Maybe I should have done that here, but it doesn't matter. It's multiplication, so that'll work. But what we notice with these two sets of answers is that every answer here is in this list, right? Because this includes that point also. So you actually don't need this. It's kind of like overkill. This is enough. This gives you the answers for both of them. It just so happens to work out that way. All right, and now what I need to do is look at where this derivative may not exist. But when you take a look at the derivative, which is here, sine is defined everywhere, sine is defined everywhere, cosine is defined everywhere. You don't have any division by 0. It's good to go. So you're not going to have any issues with this. So these are your only critical numbers. Any multiple of pi. $35. F of x equals x squared e to the negative 3x. All right, so same thing. Let's take the derivative. Let's also keep in mind we could write this way. Right, that's the same thing. So we could use product rule when we take derivative, or we could do quotient rule. It's really up to you. I think I'm going to do the quotient rule, just because I know that when I take derivative and if my answer is a quotient and I need to set it to 0, all I'm going to worry about is the top. So that's just my preference here. The derivative of this is the derivative of the top times the bottom minus the derivative of the bottom. So why is the derivative of e to the 3x 3e to the 3x? Well, I hope you know. It's chain rule on that. Derivative of e to the 3x is itself times the derivative of what's up here, which is 3, but I put it out in front. And then finish off the quotient rule times the top all over the bottom squared, e to the 3x, that entire quantity squared. Now, I need to set this thing equal to 0, but let me clean it up a little bit. Check this out. Notice on the top, I have an x here, an x squared here, so I can factor an x out. I have an e to the 3x and an e to the 3x, so I can factor an e to the 3x out. And what I'd be left with is a 2, right? There's a 2 here. And then minus, over here, what I'm left with is the 3 and one of these x's. Ooh, that's a nice. And then over, how about this? E to the 6x. So something to a power, you multiply the powers. 3x times 2 is 6x. There's my derivative. Now, I want to know when the derivative is 0. So I have a fraction, so all I have to consider is the top. So I set the top equal to 0, which means since this is multiplication, I can set each factor equal to 0. Okay, now x equals 0, well, there's nothing to do there. E to the 3x is never going to be 0. That's impossible. E to the 3x looks like this. This thing never hits the x-axis. There's no solution here. And this one right here is just a linear equation, so you get x is equal to 2/3. So far I have two critical numbers, 0 and 2/3. And now I need to check, is the derivative ever undefined? So does derivative not exist anywhere? That's the question. Well, the only issue I'm going to run into is possibly division by 0, right? Because this is a nice polynomial. That's an exponential function. This is another polynomial. It's a line. And so these things, you can plug x's into these, no problem. But can we plug an x in to make that 0? Well, that's the question. E to the 6x, can that ever be 0? No, can't. For the same reason here. Can't do it. So I don't have to worry about this. The only two critical numbers I have are 0 and 2/3. Okay, that's going to be it for right now. Continuing here. All right, so now we're going to step into the next section of this homework, number 37. The instructions here are different than what we just did. So we're going to start to put a lot of the ideas together here. So 37, we have a function f of x equals 12 plus 4x minus x squared, and they give us a closed interval, 0, 5. All right, and what they want to know is what is the absolute maximum value and what is the absolute minimum value of that function on that interval. So if we were to draw this, what would be the highest point and the lowest point if you only drew it on that interval? So there's a technique for this. It's called the closed interval method, and we did that in class, but it's also stated on page 207. So we need to have, in order to use this method, we have to have a continuous function on a closed interval, which this is a continuous function because it's a polynomial. This is a closed interval, so the method should work. So I'm going to start by taking the derivative so I can find the critical numbers. So the derivative of this is just 4 minus 2x. And to find the critical numbers, I set this equal to 0, first thing. And I just get 4 minus 2x is 0, which means x is equal to 2. So that's one critical number. And then I need to figure out if this thing is ever undefined or doesn't exist. And that doesn't happen because that's a polynomial that's never going to have any problems. You can plug any x value you want in here. Now, when I look at my critical numbers, I only have one here. I need to make sure that this critical number is in here, which it is. So since it is, the next part of the method is to evaluate the original function. So I'm going to plug into the original function both endpoints and any critical numbers I had. All right? But I'm plugging these into the original function, and I'm just going to see what I get. So if I plug in 0, I get 12. All right? If I plug in 5, I get 12 plus 20 minus 25. Let me just double check that. 12, 20, 25. So this is 32. Take away 25. I should get 7. And then if I plug in 2, I get 12 plus 8 minus 4. So this is going to be 16. And now what I do is just compare these answers. The biggest answer I get is the maximum value, absolute max, And the smallest value I get is the absolute minimum. Very straightforward. Now, this is the absolute minimum value of the function. This is the absolute maximum value of the function. But I always like to write them as points. So I have an absolute minimum at the point 5, 7. And I have an absolute maximum at the point 2, 16. So this is the x-coordinate, y-coordinate, x-coordinate, y-coordinate. Great, my computer's about to restart. Hold on. Okay, let's move on. Number 39. So the technique here, to use a closed interval method, you have to have a continuous function on a closed interval. Once you have that, you take the derivative, you'll get your critical numbers, then you just plug in the critical numbers and the endpoints into the original function, compare the answers, and you're done. It's great. Great little method. 39. F of x equals 2x cubed minus 3x squared minus 12x plus 1, and we're looking at the interval -2 to 3. Nice polynomial, continuous everywhere, so of course it's continuous on that closed interval. And I'll take the derivative, 6x squared minus 6x minus 12. Hey, is this the problem we did earlier? Oh no, it's not. It's a little different. All right, I need to take the derivative, figure out where it's 0. So 6x squared minus 6x minus 12 equals 0. I'll divide everything by 6. I can factor the left side, and I get x is 2 and x is -1. Two answers here. So I'm going to check to see if these are in here. 2 is in here, -1 is in here. If one of these wasn't in here, I would just throw it out. I just wouldn't look at it. Now, is the derivative ever undefined, or does it not exist anywhere? Well, the derivative is a polynomial, so no issues here. So now all I do is I take the original function, I plug in -2, take the original function, plug in the other endpoint, 3, then plug in my critical numbers, 2 and -1. And now you just evaluate the function. So I'm going to save myself a little bit of time. Let's see. At -2, we get -3. At -1, we get 8. At 2, we get -19. And at 3, we get -8. All right, so what is the largest value here? Well, the largest value here is 8, and the smallest value is -19. So I'm going to write it this way. The absolute minimum is at the point 2, -19. Of course, the minimum value is -19, but I like the point again because it tells us where it happens. The absolute max occurs at -1,8. All right. Not so bad. 41. Oh wait, you don't. I'll do. Yeah, 41 is so much like this one. Let me do 43, because that's your homework problem. I'm going to do that one. 43. So I did 39. I'm going to let you do 40. 43 f of t equals t square root 4 minus t squared on the interval -1, 2. All right. So we actually do have to worry a little bit about our domain here. Is this a continuous function on this closed interval? Well, we have a root in here, and we know that the root, that can present some issues. So we need to ask ourselves, can this ever be a negative number, right? Can it? Well, what about 4 minus t squared? I want that to always be bigger than or equal to 0, right? I don't want it to be negative, so this is what I do want it to be. And there's so many different ways to look at this. This goes back to what your knowledge of solving quadratic inequalities is. Let me do it this way. If I were to ask you to graph this function, treat that like an x, what would it look like? Well, you would have negative x squared, which would be a parabola that opens down. Then you'd be adding 4 to it, so it would come up 4 like this. So it'd be a parabola that looks like this. And it would hit the x-axis here at 2 and -2. And so when we say, when is this bigger than or equal to 0, we're saying, when is this graph above the x-axis? And that happens all in this region that's between -2 and +2. So the domain of f here is the interval -2 to 2. That's the domain of this function. But we're looking for the absolute maximum and minimum value of this function on this interval. This interval is actually in here. So in other words, this function is continuous on that interval because that interval is actually inside of the domain of the function. So we are free to proceed with the method. Right? So if this said something like this, we couldn't do the problem because that 4 would be outside that. All right, so let's do the derivative. I'm going to do product rule right there. There's a product. So derivative of the first one is just 1 times the second one plus the derivative of the second one. Well, derivative of the square root of something is 1/2 times the square root of that something times derivative of what's inside, -2t, times the first function. There's your product rule. I'll clean it up. Those 2's cancel. I get root 4 minus t squared minus, because that minus sign, I have t and t, so I have t squared over root 4 minus t squared. Now I know I'm going to have to set this equal to 0, so I'm going to get a common denominator now. So this over 1. I'm going to put this denominator here up on top and bottom. So when I multiply the top by this root, it's the same as this root, right? So it's going to just go, the root's going to go away. So I just get 4 minus t squared. And then I'll have the same denominator as this one, so I'll be putting them together. Then I'll have to take away t squared. So there's our combined common denominator. There it is. That's well, I can clean it up a little more. 4 minus 2t squared over root 4 minus t squared. This is our derivative. Now I want to know, when is that derivative 0? So I just set the top to 0. All right, so just move things around, divide by 2, take square root on both sides, have to do plus or minus. So I have 2 critical numbers right now, positive root 2 and negative root 2. Now I have to consider, can the derivative ever be undefined? Or could that not exist? And the answer is, yeah. If this thing is ever 0, right, we're going to have a problem. Now I don't have to worry about this ever being, the inside ever being negative, because I'm only working on the domain anyway, right? I'm inside the domain. So I don't have to worry about the 4 minus t squared being a problem as far as being a negative number. But it could be 0. If that's 0, that's a problem because I'm going to divide. So what would make this thing 0? You could set 4 minus t squared equal to 0. You'd get 2 and negative 2. So t equals positive or negative 2 would actually cause an issue with the derivative. So I have a total so far of 4 potential critical numbers. Now, how many of these critical numbers live inside of here? So remember, root 2 is about, this is approximately 1.414, approximately t. And then of course here, this is 2 answers. T is 2, t is negative 2. So which of these answers, if I'm looking at these 4, there's 2 of them here and 2 of them here. Which of these live inside that interval? Well, 2 is in there, yes. Negative 2 is not, so I'm just going to chunk it. All right, how about positive 1.414? Yes, that lives in here. How about negative 1.414? No, it does not. So I only have, at the end of the day, 2 critical numbers. The 2 critical numbers are t equals 2 and t equals 1.414. Or I'm not going to write 1.414, I'm going to write root 2. All right? Those are my only 2 critical numbers. So now I go through the process now. The last step is just to take the original function, evaluate it at the endpoints, and then evaluate it at the 2 critical numbers. Now notice that this critical number is also the endpoint, so I don't have to do it twice. I just have to do it one time. But I still need the root 2. So there we go. Those are my 2 endpoints, and that's the critical number also. And then that's my other critical number. So I plug these into the function. Let me actually plug these in. What would happen if I plug negative 1 in there? Get negative 1 square root of 4 minus negative 1 squared, which would be negative 1 times square root of, let's see, negative 1 squared is 1, 4, but take it away, so 4 minus 1, that's root 3. So this is just negative root 3. And then if I plug in 2, I get 2 root 4 minus 2 squared, which is 2 root, 2 squared is 4, 4 minus 4 is 0. Uh-oh, that's just 0. Okay, no big deal. Then this one, root 2 times root, because I'm plugging in root 2 for t, right? So root 2, and then 4 minus root 2 squared. So root 2 squared is 2, 4 minus 2 is 2. So I have this root 2 times root 2 again, which is just 2. The biggest number I have here is 2. The smallest I have is negative root 3. So we have a minimum, absolute minimum is occurring at the point negative 1, negative root 3. And an absolute maximum is occurring at the point root 2, 2. Which one was this? 43. $45. This will be the last one that I do. 45. You have f of t equals 2 cosine t plus sine 2t, and you're on the interval 0, pi over 2. All right, now is this a continuous function? Yes, of course. It's a cosine function and sine function put together through addition. So that is continuous everywhere. So that interval doesn't even matter. I've got continuity everywhere, so I'm good to go. I'm going to just take a derivative now. So I get negative 2 sine t. And then here's some chain rule, be careful here, plus cosine 2t, that's derivative of sine 2t, times derivative of what's inside, which is 2. So if I clean it up, I've got negative 2 sine t plus 2 cosine 2t. That's where I'm at. And now I'm ready to set this thing equal to 0. So negative 2 sine t plus 2 cosine 2t equals 0. And that's going to be a little bit of an issue because one of your trig functions is sine of t, the other one is cosine of 2t. You can't start messing with these. What we need to get is both of these in terms of the same argument. So we need to convert this 2t to a t. And we're going to do that using double angle identities from pre-cal. Now remember, for cosine there's 3 of them. These are on reference page, where are they? Reference page 2 at the bottom right, double angle formulas. There's 3 that I can choose from to replace this. Now I'm going to choose the one that has just sines in it because I already have a sine, and then I can factor. So I'm going to rewrite this as negative 2 sine t plus 2. Now the one I'm going to use, 1 minus 2 sine t squared. All right, so bottom of reference page 2, double angle formulas, right there, the cosine 2x. The last equation there is 1 minus 2 sine squared x, but I'm using t here, equals 0. Now, again, if you don't know why I did that, just keep watching. Let's see here. I'm going to distribute this 2 through. So plus 2 minus 4 sine squared t equals 0. So now this is starting to look a little bit better now. I have sines, just a bunch, well, I don't have a sine here, but I have sines in here. I don't have a mixture of sines and cosines. I'm going to rearrange the order. I'm going to put negative 4 sine squared t minus 2 sine t plus 2 equals 0. And I noticed that I have a factor of 2 in all of these, so I'm going to divide through by 2. I'm also going to change the signs to make this one positive, and then negative. So really I'm dividing everything by negative 2, negative 2, negative 2, and then over here negative 2. It's still going to be 0 here. But this is going to give me 2 sine squared t, and then plus, that's just a 1, so sine t, and then over here we get minus 1. Now, from pre-cal, hopefully you remember this. This is again a trig equation, but it looks like a quadratic, right? It almost looks like we have like 2x squared plus x minus 1. So this should factor, hopefully, into 2 things. It should be, let's see, let's try this. 2 sine t here. So if I multiply those 2 together, I would get 2 sine squared t. Let me try this, plus 1 minus 1. So if I distribute here to here, I get the 2 sine squared t, check. 2 sine t times 1 is 2 sine t. Negative 1 times sine t is minus sine t. So I take that 2 sine t, I take away 1 sine t, that's going to give me just 1 sine t. And then negative 1 times 1 gives me negative 1. So that is the correct factorization. And now what I can do is I can set each of those factors equal to 0. So I set 2 sine t minus 1 equal to 0. I'm almost out of room here. I set sine t plus 1 equal to 0. Let me see if I'm on camera here. I'm there, okay. So this one I get sine t is a half, and this one sine t is negative 1. And I'm going to move over here and do those. So I want to know, when is sine t equal to a half, and when is sine t equal to negative 1? Now I'm going to go to my unit circle to do this, but keep in mind that I'm not on an open interval here. I'm not looking at all the general solutions. I just need the solutions that live in here, 0 to pi over 2. So I'm really only looking in the first quadrant, right? I can throw out everything here and here, everything here and here. All right, I don't even need to consider anything outside that interval. So sine of t is a half. That means where's the y coordinate 1/2? That actually does happen. It happens right there. Okay, the x coordinate there is √3/2. The y coordinate is a half. And that angle is pi/6. So if t is pi/6, I'm gonna get 1/2. So that's a critical number. Over here, where's the y coordinate -1? That only happens down here. And that's outside my interval. So there's no solution from this. So that's my only critical number so far. I also need to consider now, is the derivative ever 0? So was the derivative, I mean not 0, was it ever undefined or did it not exist? And I already erased it, but that's not going to happen because our derivative was just sines and cosines, and those are defined everywhere. The way that it was written, there's no division by 0 possible, so I don't have to consider. So now, all I do is I take the original function, I plug in the endpoints, and then I plug in any critical numbers I had. I only had one. All right, let's plug these in. 0. Cosine of 0 is 1 times 2, so we get 2. Plus, all right, 2 times 0 is 0. Sine of 0 is 0, so that's it. 2 plus 0, that's just 2. How about pi/2? Cosine of pi/2, so pi/2 is straight up. Cosine there is 0, so that's 0. Be careful here. I'm plugging in pi/2 into this. Sine of 2 times pi/2, 2's cancel. Sine of pi. So if you go to pi, which is right there, and pick off the y coordinate, it's 0. So you get 0 for that whole thing. And now pi/6. This one's going to be a little bit trickier, so I'm going to write it out. This is 2 cosine pi/6 plus sine of 2 times pi/6, which equals 2, all right, cosine of pi/6. Remember, pi/6 was here, right? So cosine was the x coordinate, so √3/2 is this piece right here. Plus, now be careful, 2 times pi/6, the 2 and the 6 reduce out. This is really going to become a pi/3 in here. I want to know what sine of pi/3 is. So pi/3 is here, and sine is the y coordinate, which is √3/2. So this is also going to be √3/2. These 2's cancel, and you just get √3 plus √3/2. All right, I think that's good. Now, I think it's obvious what the smallest number is. This is your minimum. It's happening here. So you have an absolute minimum. It's happening at pi/2 is what you're plugging in, 0 is what's coming out. So the minimum value is 0. The absolute maximum, well, you have to compare this answer to this answer. So which is bigger? Well, you might need a calculator for that. √3, you need this to be bigger than 2. And I'll save myself the trouble. Maybe the book does it. What number is this? 45. It's about 2.6. It's about 2.6. In the book, what they do is they get a common denominator. They put this over 1. They multiply top and bottom by 2. So go 2 √3 plus √3/2, like that. That's a common denominator. And then they say, okay, 2 √3s plus 1 √3, that gives me 3 √3/2. But it doesn't matter, because if you get on your calculator and you figure out what this is, it's approximately 2.6. And that's bigger than 2. So your absolute maximum is going to occur when you plug in pi/6, and it spits out, I'm going to leave it the way we had it, √3 plus √3/2. All right, you should look at some of the problems close to these, like, 44, 46, 47, 48, 49, 50. Those are all good problems. All right, that's it.